Right now, a bubble could be racing toward Earth at the speed of light. Inside it, atoms as we know them cannot exist. No telescope can see it coming because nothing in the universe outruns it. The first evidence of its arrival would be the arrival itself. This is not science fiction. The idea comes from two numbers physicists have already measured. The first number is the mass of the Higgs boson, about 125 in the energy units of particle physics. The Higgs boson is a ripple in the Higgs field, an invisible field that fills all of space and gives fundamental particles their mass. The second number is the mass of the top quark, the heaviest particle we know, about 172. Once the Large Hadron Collider pinned down the Higgs mass in 2012, theorists could put both numbers into the equations that govern the Higgs field and ask a harmless-sounding question. Is empty space sitting in its lowest possible energy state? The answer? Maybe not. Here is the picture those equations draw. Think of the energy of empty space as a landscape, and the Higgs field as a ball resting in a valley. Our valley has held for 13.8 billion years, but according to the central calculation, it may not be the deepest one. Far beyond any field strength an experiment can reach, the landscape plunges into a deeper valley. A vacuum like ours has a name, a false vacuum, and quantum mechanics gives it one strange weakness. The field does not have to climb over the ridge. A tiny patch of space can tunnel straight through it. When that happens, a microscopic bubble of true vacuum appears inside our false one, and a competition starts. The bubble's wall costs energy, and for a tiny bubble, the wall is nearly all there is, so almost every bubble shrinks and vanishes. But if one ever forms past a critical size, the energy released by its growing interior beats the cost of its growing wall. From then on, it only expands. The wall accelerates, feeding on the energy difference, until it is moving at essentially the speed of light. Everything you are made of depends on the value the Higgs field holds. Electrons weigh what they weigh because of it. So this wall is not a blast wave. Space behind it runs on different rules. Cross the wall, and fundamental particles change mass. Atoms as we know them cannot form. Chemistry stops working. Exactly what the inside would look like depends on physics no one can test. But nothing built from atoms survives. That summary is safe. And here is why there could be no warning. Any alarm, light from dying stars, radiation from the wall itself, travels at light speed at best. The wall moves at essentially that same speed. Nothing can pull ahead of it to deliver the news. On a space-time diagram, the bubble and its own first light ride the same line. The universe could have ended somewhere years ago, and tonight's sky would look completely normal. For 50 years, that was where this story stopped. Vacuum decay stayed a calculation. Elegant 1970s mathematics by Sidney Coleman and others, describing an event no one could ever watch. That changed in 2024, in a lab in Trento, Italy, inside a cloud of atoms colder than deep space. The team trapped about 1 million sodium atoms and chilled them until they merged into a superfluid, a state of matter where the whole cloud flows as one quantum object. They tuned the cloud so that the state it started in was metastable, a false vacuum made of atoms. Then they waited and watched. Nothing. Nothing. And then, at a random moment, a patch of the cloud flipped. A bubble of the true state appeared and spread. Rerun it, and the bubble appears at a different time, in a different spot. The roll of the dice behavior tunneling theory predicts, at rates matching the same mathematics Coleman wrote down for the cosmos. Published in 2024, this was the first time false vacuum decay had been watched happening in a real physical system. Then a second window opened. In February 2025, a different team ran the same physics on a quantum annealer, a machine with 5,564 superconducting qubits linked in a ring. Every qubit started aligned, a programmable false vacuum. As the machine evolved, domains of flipped qubits appeared, quantized bubbles of true vacuum, some more than 300 qubits long, forming in real time. The simulation even caught bubbles interacting. A large bubble can feed on a smaller neighbor, growing while the other shrinks. Neither experiment touched the Higgs field, and neither could endanger anything. They are scale models, real quantum systems obeying the same equations. But vacuum decay is no longer only a story told in mathematics. It is physics you can watch on a bench. So how seriously should you take the bubble? Start with the time scale. If the standard calculation is right, the expected lifetime of our vacuum is 10 to the power of hundreds of years. Not hundreds of years. A 1 followed by hundreds of zeros. The universe today is a 1 with 10 zeros. Star formation runs out around a 1 with 14. The last black holes evaporate near a 1 with 100. Put those on one chart, and every other ending of the universe happens first. And vacuum decay's deadline still is not close. Second, the verdict itself sits on a knife's edge. Plot every possible universe on a chart. Higgs mass along one axis, top-quark mass along the other. In one region, empty space is truly stable, forever. In another, it is metastable. Our measured point lands in the metastable zone, but barely. And the uncertainty around it, driven mostly by the top-quark, crosses the boundary line. Our vacuum is metastable, within error bars of being perfectly stable. Move the top-quark's mass by less than 0.5%, and the verdict flips. In 2025, a survey finally asked the experts directly, is our vacuum actually metastable? Across 20 physicists who work on this, the average answer was about 45%, a coin flip, with individual answers running from nearly zero to near certainty. That spread is the real finding. The verdict depends on stretching our current equations to energies trillions of times beyond anything ever tested. So the question is really whether the standard model, our rulebook for particles, survives that whole journey unchanged. Nobody knows. One more entry, because the internet keeps asking, could a particle collider set this off? No. And the answer is an observation, not a promise. Nature runs far more violent collisions than we do. Cosmic rays, atomic nuclei accelerated across the galaxy, have been slamming into the Earth, the Sun, and every neutron star at energies far beyond the Large Hadron Collider for billions of years. If ordinary collisions could puncture the vacuum, the universe would have shown us long ago. It is still here. So here is what metastable actually means. It is not a prophecy. It is a statement about where two measured numbers land inside our current equations. Equations that are probably not the final word. A future collider that pins down the top quark's mass could push our point cleanly onto one side of the line, maybe the stable side. Until then, something genuinely strange remains. Of all the values those two masses could have taken, the ones we measure land almost exactly on the border between a universe that lasts forever and one that is quietly temporary. Empty space is keeping that answer to itself. But now we know what the ending would look like, because we have watched it happen, in miniature, on a table.